So welcome. We now want to look on partial fractions. So we want to start to build the foundation and the knowledge of partial fractions. So let's just start off. In our primary, we could be asked, for example, to solve So this is how we will be asked. We want to solve this equation. So this equation we just now first we find the LCM, which is then this one will be then now of course the constants. So we solve it to be then now expanding the denominator we can have it as this one. So therefore we can now write our equation to be right. So this is what we were doing in our R primary. So these ones and this one are the partial fractions of this expression. So if we say that this is A, B, and C, then A and B are the partial fractions of C. Now at this level now, we want to learn of how now we can split this expression into its partial fractions. So in summary, that is what fractions, that's what partial fractions are. These are the numbers or the fraction that an expression like this can be split into. So we're going to look on three classes of partial fractions, and the first one being these simple partial fractions such as this one. So our first class of simple partial fractions, let's start. So in handling simple partial fractions, I want us to use this same example so that you can be able to learn the process. So for example, if you are asked to express 8x minus 40 over x squared minus 8x plus 12 in its partial fractions. Now before you split this equation or this expression into its partial fractions, there are some things that you should consider. First, you should ensure that the degree of the denominator is greater than the degree of the numerator. So the degree or the order of this polynomial in the denominator is 2, and the degree of the numerator is 1. So that is okay. The second factor that you should consider, you should check whether this equation in the denominator is factorizable or not. And the test if this equation is factorizable, we say it is by using. So by taking b squared minus 4ac to be k, and the k is a real number. If it gives you k, which is a real number, then it means that that expression is factorizable. That is for the case of the quadratic expressions like the one we have. So let us carry out the check. If we take the square root of 8 squared minus times 1 times 12. So remember, this is our A, this is our B, and this is our C. A is the coefficient of x squared, B is the coefficient of x, and C is the constant. So by checking this, we have found to be 4. So that means that this expression is factorizable. In other situations where the expression is not factorizable, there is a way we will do it in the methods that we are going to learn further. So we therefore continue to this step 2. So because we have now identified that this expression is factorizable, then now let us factorize it. So yeah, we find two numbers whose product will give us 12 and whose sum will give us -8. And usually these numbers are -6, -2. So we express it as, so by taking each of the two numbers, we factorize them. So yeah, becomes this. Yeah, please also I would like to remind you that the methods of factorizing quadratic equations we had already handled. But please check it out in our channels. The video is right there, and subscribe. So okay, we now write it then as x. Yeah, after now we have factorized the denominator, we have this equation. So therefore, this equation, we can present it in this form, whereby a and b are real integers. So we want now to find a and b. So as we had said, these are now the partial fractions of this expression. But now we want to find the specific values for a and b. So this one, we assume that we don't have this expression. So we write, so we want now to solve this equation. So it will be here we then now simplify and factorize the numerator. So it becomes, so this equation or this expression, we equate it with our original expression. So it will be like, so since these expressions are just equal, then now let us now equate the numerators. So by equating the numerators, we now establish the relationship that the sum of the coefficients of x on the left side will equal to the sum of the coefficients of x in the left side. The sum of the constants on the left side equal to the sum of the constants on the right side. So we write the equations as, so we now develop as simultaneous equations. So we want to find these values by using elimination method. Let us multiply this by -6. We have, so subtracting these values, we have the form b equals to -8. So we now have our values for b and a. So therefore, our expressions will now be, so that is the same expression that we had at the beginning. So this is the method of splitting this expression into its partial fraction. So I want us to look at the second example. Here now we want to find the partial fraction of this expression. So we carry out the checks that we had said. So the first check, if we look, we can see that the degrees of these equations are equal to the denominator and denominator. So before we start, we should ensure that the degree of the denominator is larger than the degree of the numerator. So what can we do? So what we will do here, we carry out long division. So in carrying out the long division, we take the coefficients of x squared and the x squared. So here this 1, 1. So we can choose constant 1. So 1 multiplied by this expression gives us, so we subtract, we have 5x 7. So in other words, we can express this expression as, so it is just the same way as we can express mixed fractions. Yeah, so the second step now is to check whether this denominator will be factorized. So let us carry out a check. So by carrying out, we have 4 which is a real integer. So that means that this expression can be factorized. So that one makes us to express this expression as. So we can also further express it as, and then now we are required now to find the constants a and b. So yeah, so because this expression is just equal to this expression, then now we equate the numerators. So here we want to use a simple method to solve. So if we take x to be 3, b will be 0, and this will be, yeah, so we'll find our a. And if we take our x to be negative 1, a will be 0, and this will be, and our b will be 3. So we can now express this equation as. So now, coming back to our original equation, then we will have it this way. This was our equation, so it becomes this one. Okay. We want to look on the second class partial fraction, in which the denominators have irreducible quadratic functions. Here we say, if an expression has a denominator that is an irreducible quadratic factor or expression, its partial fraction will be the form ax plus b over ax squared bx plus c. So where this is now the irreducible quadratic expression. So that is the general expression. So we want to see this using an example. So let us see our example 1. So we want to express this expression in its partial fraction. So we want to evaluate whether this quadratic expression is reducible or factorizable or not. So we said our test is, when we carry out this test, we find this number, which is not a real integer. So that means that we cannot factorize this expression. So meaning, according to this rule, this expression can only be expressed as. So this can also be expressed further as. So because this expression and this expression are just equal, we can therefore equate their numerators as. So yeah, we should use just simple elimination methods to find the unknowns. So let us take x to be 4. If we take x to be 4, then this one will be 0. So it shall be, so 11. So our a goes to 3. Yeah, the same case, if we take x to be 0, we have, but now our a is 3. So therefore, right. So finally, let us now take our x to be 1. We have, so substituting the values of a and c, we have, so we also get our b. So rewriting this expression now from our original expression, we have, so this was our original equation. So we substitute just the values to find it this way. Well, so now we proceed to the third class of the partial fraction. So here we have the denominators with repeated factors. So we see, if an expression has a denominator of the algebraic expression with the form ax plus b raised to the power of n, its partial fractions are expressed in this form. So we will just illustrate this using an example. So we want now to express this expression in its partial fractions. So because this denominator is a repeated factor of 2x minus 3, we can now present this expression as, so we can further write it as, so because this expression is equal to this expression, we can therefore equate their denominators. So by using the quadratic identities, we can expand this expression as, so expanding further and putting like terms together, we have, so the total coefficients of x squared on the right side should be equal to the total coefficient of x squared on the left side. The total coefficients of x on the right side should be equal to the total coefficients of x on the left side. In the same case for the constants. So we develop these equations as, so yeah, solving one after the other. From this first one, we find that the 1 is 5. The second one, we find that the 2 is 3. And going to the third one, we have minus 1. So therefore, we can write our original expression as, so that is how we can handle partial fractions of any form. So continue subscribing to our YouTube channel for you to continue learning such nice topics of mathematics as such, and share to your friends. Thank you so much for watching.